Hello viewers, uh, today's lecture is based on some solved problems on Lagrange's mean value theorem. Viewers, in my previous video I have discussed in detail regarding the concept of Lagrange's mean value theorem. Uh, for those viewers who could not attend my video, I am here giving a brief introduction of Lagrange's mean value theorem. Let y equal to fx be a real function which is defined in this interval. Clear? Now Lagrange's mean value theorem says that if this function is continuous in interval a comma b, and it is derivable in open interval a comma b, and then there exists a value c which belongs to this open interval a comma b such that f prime of c is equal to fb minus fa over b minus a. Clear? So here's let y equal to fx be a function which is defined on the interval a comma b. The domain is this interval, and this function is continuous on the closed interval a comma b and differentiable on the open interval a comma b. Then there exists some c in open interval a comma b such that f prime of c is equal to fb minus fa over b minus a. So this was discussed in my video on Lagrange's mean value theorem. So viewers, let us solve some more problems on Lagrange's mean value theorem. So here we have the problem, verify Lagrange's mean value theorem for fx equal to x square in 2 comma 4. So here we have if we compare this with a comma b, then we have a is equal to 2, b equal to 4. Clear? Now the first condition is this function fx is continuous. Why? Because it is a quadratic function, or we can say it is a polynomial function, and all polynomial functions are continuous in their domain. Clear? So therefore fx is continuous. Second is, if we differentiate it, we get 2x, and we see that fx is differentiable in 2 comma 4, and here fx is continuous in 2 comma 4. Clear? So the derivative of f is 2x, and this shows that it exists in this interval. So then Lagrange's mean value theorem says that there must exist some c belonging to this 2 comma 4 such that f prime of c must be equal to f4 minus f2 divided by 4 minus 2, because here a is 2 and b is 4. So f prime of c can be written as 2c. F of 4 is here 4 square, and f of 2 is 2 square, and 4 minus 2 is 2. So here's this is 16 minus 4 over 2 this is 12 by 2, that is 6. So 2c is equal to 6. This implies c is equal to 3, and 3 belongs to 2 comma 4. Thus we can say that the Lagrange's mean value theorem is satisfied for fx equal to x square in this interval 2 comma 4, because this value 3 lies in this interval 2 comma 4. Clear? So let us take another problem. Now viewers, here we have the problem: verify Lagrange's mean value theorem for fx is equal to square root of x square minus 4 in this interval 2 comma 4. So here also we have a is 2 and b is 4. Clear? Now the first condition, that continuous fx is continuous in interval a comma b. So here's from this function fx equal to x square minus 4, this is a square root function, and we see that this function fx is defined for all x belonging to this interval 2 comma 4, and this shows that fx is continuous in 2 comma 4. Clear? So this function, which is a square root function, is defined for all x belonging to 2 comma 4, and this shows that fx is continuous in 2 comma 4. And the square root function, since x square minus 4, here fx is valid for all values of x which belongs to this interval, so this square root function is continuous in this domain. Therefore we say that fx is continuous. Clear? We can also prove its continuity by finding out the left hand limit and right hand limit in this interval. Clear? And then we will apply the concept of continuity in an interval. Clear? Now the second point is, this function fx is derivable in open interval a comma b. Clear? So we will find the derivative of f prime fx, that is f prime of x. So and the derivative of x square minus square root of x square minus 4 is half of square root x square minus 4. This is multiplied 2x by chain rule. Then we have 2 get cancelled, and we have x over square root of x square minus 4. So whereas this implies that f prime of x exists in open interval 2 comma 4. So these 2 points are not included here. That's why this function becomes differentiable. Clear? So here in point number 1, I would like to mention one more thing, that this function is defined at the endpoints also for f2 and f4. Clear? So f prime of x is x over square root of x square minus 4. So f prime of x exists in 2 comma 4. Clear? Now the Lagrange's mean value theorem says that the function is continuous and differentiable. Then there exists a c belonging to 2 comma 4 such that f prime of c is equal to f4 minus f of 2 divided by 4 minus 2. Clear? So whereas f prime of c implies your here we will substitute the value of x equal to c, because f prime of x is given by x over square root of x square minus 4. So we have c square root of c square minus 4, and this is square. Here we have square c square. Clear? This is c square and equal to f of 4. So here we can calculate f of 4. F of 4 is 4 square minus 4, which is 16 minus 4 root 12, which is equal to 2 root 3. Clear? So we have 2 root 3 minus f of 2. F of 2 is square root of 2 square minus 4, which is 0. Clear? So we have 0 here and divided by 2. Clear? So viewers, we have c divided by c square minus 4 is equal to, here we have 2 root 3 over 2, 2 get cancelled, and we are left with square root of 3. Clear? Now we squaring both sides, we have c square divided by c square minus 4 equal to 3. Clear? So we solve it. This is c square, this is c square minus 12, 3 times c square, 3 4s are 12. So I am doing it here now. We have c square minus 3c square equal to minus 12 here, minus 2c square is equal to minus 12, so c square is equal to 6. Clear? So minus minus get cancelled and c square is equal to 6. Now c can be written as square root of 6. Clear? And here we have plus minus sign. So we see that c is equal to plus 6 belongs to this interval 2, 4. Clear? Because the square root of 6 is 2 point something, and it obviously lies in this interval. And c equal to minus 6 does not belong to 2, 4. So therefore the Lagrange's mean value theorem for fx equal to square root of x square minus 4 in 2, 4 is verified for c is equal to plus square root of 6. Clear? Now let us take one more example. Now viewers, let us take this problem. Here we have to verify Lagrange's mean value theorem for fx equal to log x in the closed interval 1, e. So the first point is this function fx is equal to log x is continuous, because the domain of log x is the set of positive real numbers, and here we have the interval 1, e, which is a subset of this set of positive real numbers. So the logarithmic function is continuous in this interval. Clear? So we can directly apply the result that logarithmic function is continuous in its domain, so is log x. Clear? Now the second one is we find the derivative of this function. So the derivative of log x is 1 over x. Now we see that this derivative exists in this interval 1, e, because e lies between 2 and 3. Clear? And the approximate value of e is something 2.71. So the interval, our interval is 2.71. So obviously this derivative f dash x or f prime of x exists for all x belonging to this interval, which is 1 comma e, and here we will use the open interval and 1 comma e. Clear? So therefore fx is differentiable in 1 comma e. Clear? So therefore fx is continuous, fx is differentiable, therefore there must exist some c belonging to 1 comma e such that f prime of c is equal to fb. Here a is 1, b is e. So f of e minus f of 1 divided by e minus 1. Clear? So f prime of c is given by this expression. So we have 1 over c, and here f of e means log of e minus f of 1 means log of 1 divided e minus 1. Now log of e is given as 1 because the value of log e is 1 and the value of log 1 is 0, so we have e minus 1. So we have 1 over e minus 1. Clear? So therefore we can write c is equal to e minus 1. We take the reciprocal here because we have 1 over c is equal to 1 over e minus 1. So we take the reciprocal. So this is the value of c, and the value of e is 2.71 approximate value, and if we subtract 1 we get 1.71 approximately, approx. Clear? And obviously 1.71 lies in this interval. It lies in 1 comma e. Clear? Hence the Lagrange's mean value theorem for this function fx equal to log x in 1 comma e is verified, and the value of c is e minus 1. Clear? Now viewers, we have this problem here. We have fx equal to x times x minus 2, and the given interval is 2 comma 3. Clear? So let us verify the mean value theorem. So here we see that fx is your x square minus 2x, and it is a polynomial function. It is a polynomial function, and all polynomial functions are continuous. So therefore fx is continuous. Fx is continuous in 2 comma 3. Clear? This is the closed interval. Clear? So fx is a polynomial function. This is a quadratic polynomial, and it is continuous. So fx is continuous in 2 comma 3. Now if you find the derivative f prime of x, so we get 2x minus 2. Clear? And see this exists in 2 comma 3. Clear? So here we have a is 2, b is 3, and the function fx, therefore fx is differentiable in 2 comma 3. Clear? Now therefore then there exists some c belonging to 2 comma 3 such that f prime of c is equal to f3 minus f of 2 divided 3 minus 2. Clear? So f prime of c can be written from this expression. So we have 2c minus 2 is equal to f of 3. Here we can find f3 is 3 times 3 minus 2, that is 1, so it is 3. And f of 2 is 2 times 2 minus 2, 0, so it is 0. Clear? So f of 3 is 3, this is 0, and 3 minus 2 is 1. Clear? So 3 minus 0 is 3, 3 over 1, which is equal to 3. So therefore 2c is equal to 3 plus 2. We take this minus 2 to this side. So 2c is equal to 5. Clear? So where c is equal to 5 by 2, which is 2.5. And 2.5 belongs to the open interval 2, 3. Hence, the Lagrange's mean value theorem for this function fx equal to x times x minus 2 in the closed interval 2, 3 is verified. Clear? Now viewers, we have one important and interesting problem here. Show that the Lagrange's mean value theorem is not applicable to this function, the absolute value function on minus 1 to 1. So viewers, we know that the graph of absolute value function is or it looks like this. This is the graph of fx equal to mod of x. Now say here we have minus 1, and say here we have plus 1, and here we have 0. Now we have this interval minus 1 to 1. Now we know that the absolute value function fx is equal to mod x is a continuous function, in its domain R, which is the set of real numbers. And this interval minus 1, 1 is a subset of the set of real numbers. Clear? So here we see that this function and the absolute value function is continuous in this closed interval a comma b. So we write that fx is continuous in minus 1 to 1, but we know that this absolute value function is not differentiable at x equal to 0. Clear? And 0 lies in this interval, and 0 belongs to this interval. We can write it like this: 0 belongs to minus 1 to 1. Clear? So we see that this function, the absolute value function, is not differentiable at x equal to 0, and the non-differentiability means f prime of 0 does not exist. Hence this condition, the second condition of Lagrange mean value theorem, is violated here, and it is not satisfied. Therefore we can say that the Lagrange's mean value theorem is not applicable to this absolute value function mod x on minus 1 to 1. Why? It is continuous, but the derivative of this function at this point 0 does not exist. It means the left hand derivative is not equal to right hand derivative, and we have seen this in our earlier videos and we have proved this result in our video on relation between continuity and differentiability. So here we have seen that the continuity of mod x, the function mod x is continuous in this interval, but this function mod x is not differentiable in this interval, open interval -1 to 1, and f prime of 0 does not exist. So therefore the Lagrange mean value theorem is not applicable. Clear? Viewers, now we have one important application of Lagrange's mean value theorem, and it says that using Lagrange's mean value theorem, find a point on the curve y equal to x square where the tangent is parallel to the line joining the points 1, 1 and 2, 4. Now here the curve is y equal to x square, or the function y is equal to fx is equal to x square, and it is a parabola. It is a parabola and it is an upward parabola. Okay, so we have a function like this here. Now using mean value theorem, find a point on the curve where the tangent is parallel to the line joining the points 1, 1 and 2, 4. So say this point is A and this point is, say, B. Say this point is 1, 1 and B is 2, 4, and say the tangent is now the parabola is given by this curve here, and we have this point A as 1, 1 and B as 2, 4, and where the tangent is parallel to the line joining. Suppose we join this the points A and B. A is your 1, 1 and B is your 2, 4. Clear? And we have to find a point on the curve where the tangent is parallel to the, so say this is the tangent and say this is the point P. Clear? And if this point is, say, x1, y1. Clear? So here we will apply the Lagrange's mean value theorem. Now if I take, instead of x1, if I take this point P as c, y1. Clear? The x coordinate is taken as c. So we have f prime of c is equal to fb minus fa divided by b minus a. Clear? Now fb, here we have a as 1, and this point is a and this point is b. Clear? So this is a and this is b. So we have the interval 1, 2. So now we have a function fx equal to x square, which is a parabola, upward parabola, and here the interval is 1, 2, and we have to find f prime of c equal to fb minus fa over b minus a. So now we'll satisfy the condition of Lagrange's mean value theorem here. Fx is continuous, y continuous, because it is a polynomial function or quadratic function. Clear? It is a quadratic polynomial, and every polynomial function is continuous in its domain. So this function fx is continuous in 1, 2. Clear? Now the second condition is we find the derivative of f, which is 2x, and we see that it is clear that this exists in 1, 2. Clear? So here's Therefore, there exists a C belonging to 1 comma 2, and this is the point C here. So C belongs to 1 comma 2 such that f prime of C is equal to fb minus fa over b minus a. Clear? So let us find here f prime of C can be written as 2C. Clear? And fb is f of 2 minus f of 1, because b is 2, a is 1, over 2 minus 1. So 2C is equal to f of 2. F of 2 is 2 square, f of 1 is 1 square, and 2 minus 1 is 1. Okay? So we have 2C is equal to 2 square 4, 4 minus 1, and this is equal to 3. And this implies C is equal to 3 by 2. Clear? So we have got C equal to 3 by 2. Now this point C lies on this curve, y equal to fx equal to x square. So therefore the value of y1 is, we have got C equal to 3 by 2. So this equation must satisfy this point. So we have y1 is equal to C square, and y1 is C square. C is 3 by 2 square, which is 9 by 4. Clear? So therefore the required point P is 3 by 2 comma 9 by 4. So this is the point 3 by 2 comma 9 by 4 where the tangent, this is the tangent is parallel to the chord. This is the chord or secant line. Clear? So this tangent is parallel to the line segment joining the points A and B. So this is how we find the point. So in today's lecture we have discussed some important problems related to Lagrange's mean value theorem. In our next lectures we will discuss some more applications of derivatives. Till then, goodbye.